This is part 13 in a series of videos in which I'm developing this. It's a drop-in replacement for the cassette drive on the Fluke 9010A microsystem troubleshooter. And the idea is it's just a direct plug-in replacement for the original cassette drive. But of course it doesn't require the cassettes. And that was really the driving force that motivated me to do this, is the tapes were becoming very hard to find, and of course that makes them expensive, but also they're fairly slow and unreliable. So I developed this in the previous videos. You've seen me prototyping it on a breadboard, getting the prototype boards made, and then building up the first prototype unit and starting to test it. I've since completed the firmware for this, and the main changes between the version I've shown before and this is this now has all the features. So it supports the external memory cards and the various bank switching, which I'll demonstrate in a few minutes. But also I've changed the way that the EEPROM is addressed. So previously I was using what's called random byte writing, so I was writing a single byte at a time to the EEPROM chip and just streaming it from the Fluke through this board to the EEPROM. That's not a good way to use these, and I thought I'd explain in this video why that's not the right way to use these and why I've changed it. So I'll get the Fluke out of the way and just briefly explain what the advantages are for changing the addressing mode on the EEPROM. Okay, so internally the EEPROM's a very simple device. It's got a memory array, and I should point out these are EEPROMs, they're not SRAMs, and that's the key to the point I'm trying to make here. So you have a memory cell array, and then there's a buffer, and then there is some control logic that controls the way that these are used. And then we have the interfaces to feed data into the device. Data comes in, goes through the buffer, and is written into the memory cell array. And then there is various control logic to control this, along with address decoding. And in general, the buffer is the size of what's called a page within the memory cell array. And so each time you write a page of data, then you essentially end the data transfer into the memory device, and that causes the data to be transferred from the buffer into the memory cell array. And because this is an EEPROM, there is a limited number of times you can do that for the life of the device. Now it sounds quite high when you look at the spec sheet. It's around 1 million write cycles, erase write cycles for this particular device that I'm using, which is fairly typical for these EEPROMs of this type. But while 1 million sounds a lot, what you have to remember is if you do random byte writes, that is if you write just a single byte somewhere in the page, and then write the data through to the memory cell, then for every byte within the particular page, a complete erase refresh cycle is performed. So if you write sequentially into the device, then on this particular device, and on most devices like this, the page size is 128 bytes. So what you end up doing is you create 128 erase write cycles every time you fill up the buffer. So that is, if you write a single byte to the buffer and then you terminate the process, the device internally transfers the data from the buffer into whichever page you're looking at, you're addressing, but every cell within that page has a read-write or erase-write function performed on it. So for a single page, if you write the bytes individually, that's 128 erase write cycles for a single page of data. And because if you lose a single cell within a page, you effectively lose the entire page, then the first page to fail in the device is generally what terminates the use of the device. So when you divide 1,000,000 by 128, then obviously the number of erase write cycles starts to come down very rapidly. And in fact it equates to around 8,000 cycles. That's 8,000 page reads and writes. And that's obviously not very many when you're talking about the lifetime of a particular device. So in other words, it's a very bad idea writing bytes one at a time into these devices if you intend to use them for bulk data storage as we're doing here. Alternatively, if you write a whole page before you terminate the process, then you only perform one erase write cycle for every 128 bytes that you write into the device. In other words, it will last 128 times longer. Also, the process of writing data from the buffer to the memory cell array takes several milliseconds, and that means that if you're doing this thousands of times for a particular store function, then it can take quite a long time, in the order of tens of seconds, to write a lot of data to these devices. And again, if you're only doing that once for every 128 bytes of data, it effectively runs about 120 times faster. So that's the reason for using page writes rather than individual random byte writes. It extends the life of the device by a factor of about 128, and it's 120 or better times faster. So that was the reason for changing to page writes. That does make the firmware much more complicated because you have to keep track of where you are within a particular page, and it's unlikely your data is always going to be 128 bytes, but sometimes it might be 128 bytes, so you have to deal with corner cases, and it does make the firmware much more complex to write and to develop. In the same way with reading the device, it's a bit more straightforward, but is much more efficient if you use serial read mode. So rather than reading one byte at a time where you have to send the address you want to read to the device, if you can just write the address of the first byte you want to retrieve and then just sequentially use the internal counter within the control logic of the device, it means the amount of serial communication between your system and the EEPROM is much less, and you get a much more effective and efficient system. Okay, so that's what I've done with the firmware. I'll get the Fluke back on the bench and we'll have a quick look at it, and hopefully you'll see that it's now faster than it was in the previous video. Okay, so we'll power up the Fluke. As ever, apologies for the flickering display. Someone did ask if I could extend the shutter speed on the camera to prevent it, but unfortunately no, I can't do that with my camera. It's automatic and it's not an adjustable setting, and in fact the shutter speed varies depending on what's in the field of view, so you will see it varies over time. What I will do is turn down the lights in here. There is an interaction between my LED lights and the display on here, and the camera does get confused and tends to flicker more with the lights on. Also, if I turn the lab lights down, we'll be able to see the LEDs on the memory board more clearly. Okay, well hopefully you can still see what's going on okay, and the important thing here really is the switch down here and the LEDs. So firstly, one of the features I've implemented now is write protect. If we slide switch 2 up and then try and write the tape, notice we get a write protected message. If I turn that back off and hit write, you can see that we now can write if we want to. So what I'll do first is actually read this to get some data into the Fluke. And what you'll notice is it's very much faster than it was previously. There is quite a lot of data actually in here, this is the same amount of data that was in the previous video. So if we look at the various programs, you'll see that some of the programs are quite large. There's about 1,000 bytes worth of program data, but even so you can see it writes fairly quickly, or at least it reads fairly quickly. Where we really start to win out now, having moved to page writes, is how much quicker it is when it's writing. So we'll write this data back to the memory card, and as you can see, it is 4 or 5 times faster writing like this than it was previously. I've also implemented all the other features for different banks, so we'll select a different bank, we'll read that bank. There's even more data in this one, and so if we look at some of the programs, we'll see that there are some fairly lengthy programs in here. So as I said, the main advantage in terms of operation with page writes and page reads is that it is very much faster when it comes to writing the data to the memory chip and reading it back. So this is now complete. I've got all the firmware as far as I intend to take it for the first release. What I'll be doing with supplying these is I'll be supplying a bare board and a program to pick, or a bare board, program to pick, and the made up ribbon cable, and then I'll leave it up to the builder to get the rest of the parts to make their particular unit. Quite low cost. It's the actual part count is very low, and they're all fairly cheap parts, so the cost to build one of these will be very low. The cost of the memory cards will also be very low. I've got some on order now, and as soon as they come in, I'll put one together and we'll demonstrate that as well. If you're interested in one of these, let me know. They should be appearing on my website before too much longer, and as I say, hopefully it will make quite a nice addition to anyone that has a Fluke. This is intended only as a replacement for the cassette drive, so I won't be making a link to PCs or anything like that. It's not what it's for, and also I don't want to have to start cutting holes in the Fluke or modifying the Fluke firmware to make use of this. You can move programs from one unit to another using the memory cards, and that's what they're for, but I won't be making an interface between this and a PC. If you need to do that, there is an RS-232 interface that's available, and that's what that's for. Any questions or comments, please let me know. But as I say, hopefully this will make the scripting for the 9010A much more accessible to most people, rather than having to go through the long-winded process of typing these programs in.